So today we're going to look at periodic functions, and then we're going to continue that into what the sine function looks like. So a function is considered to be periodic if it has a pattern of y values that repeat at regular intervals. So it's that repetition that really matters. One complete pattern is called a cycle, and a cycle may begin at any point on the graph. The horizontal length of one cycle, so this horizontal distance here, we're looking at is called the period. Okay, when we talk about waves and wave functions, we would turn that into wavelength. For the purposes of our course right now, we're going to call that our period. So what does that mean? So here I have one cycle. So there's one pattern. Notice how it repeats itself. It's there. If I continued it, it'd go that way. There's part of it there. So there's one cycle. The period is the length of that. So how far across it is on our x-axis. So from start to end, it goes 1, 2, 3, 4. So my period would be 4 units. Okay. So the period is the interval needed to complete one cycle. And a cycle is a series of events that are regularly repeated, starting from one point and returning to the same point in the same way. So it's repeating the same pattern. And we're going to look at a bunch of these right now. Okay, we've got the time of sunset. So here I have a nice curvy repetitive pattern. So it's showing how the time of sunset varies over a 2-year period in Ottawa, Ontario. So this is definitely a periodic function because I can see repetition, right? Repeats itself. So what's the period of this graph? So you kind of have to find 2 points that match. So either 2 bottom points, midpoint to midpoint, maybe top to top. So you kind of have to pick values that are nice and easy to read, right? And that give you numbers that you can work with, right? So if I go maybe from, let's go from here, and then there's a full cycle up and around, and then it ends there. So they're both at the same y-axis point. So we got to look to see for a period. So for the period, I would say 629 minus 264. So what does that equal? So that's 365. Okay, did I have to do those ones? No, I could have picked other ones. I could have maybe gone from here and said that my curve continues and ends there. So for this one, I would have done 445 minus 80, and what does that give me? 365. So regardless of where I went, as long as it's one complete pattern, I can figure out the period of this graph. Here we have one where I'm talking about the length of shadows. So it shows how the length of a shadow, I think that's supposed to say object, oops, of a 100-meter object varies over a 3-day period. So you see there's no shadow, and then it's really long to 0, really long again, nothing, really long, 0, really long, nothing, really long, 0, really long, nothing. Well, that's kind of an interesting curve, isn't it? So here we can see that if I say started with this point, my curve is going down, up, end, repeat, down, up, end, repeat, down, up, end. So I want to go to figure out my period. I need to figure it out from when it goes from one point to the next corresponding point. So this is a really funny scale. I don't know what textbook this came out of, but it's a really funny scale. And it looks like it's following a 24-hour period, right? Because it's the day. So go from 6 a.m. to 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 6 a.m. So that's what that one looks like it's doing. How about here? We got blood pressure and volumes. So this graph shows how the pressure and the volume of blood in the left ventricle of the heart varies over 5 consecutive heartbeats. So what is the period of this graph? So let's see. If I look at my maximums here, it starts there, down, flat, up, down, flat, up, down, flat, up, down, flat, up. So each one of those is part of the pattern. So I'm repeating my pattern. Okay, it's not a nice, easy, necessarily graph to read. So each repetition is happening that way. So we got to figure out what each of these grid lines represent. So on the x-axis, let's see, I've got 5 grids. And 5 grids totals 1. So what's 1 divided by 5? Well, that's 0.2. And then if I look, I see I've got each pattern goes over 4 grids. 4 grid lines times 0.2 each grid line. So my period is going to be 0.8 seconds. Okay, so sometimes you have to pay attention to what the grid is showing you. And ditto down here. See, I have a max, I have a max, I have a max. It's a cooler shape, but it's still repeating every 4 grid lines, same scale, so 0.8 seconds. Cool. All right. What else we got? Here I have a grid. It's got a cool pattern happening here. Up, over, down, up, over, down, up, over, down. All right. So let's see, up, over, down. So I repeat myself. I'd say this is all one cycle here. So there's one pattern. So my period, so I'm going from 0 to 7. So I say my period is 7. And then I just want to figure out the function when x is equal to 4. Remember that's, I mean, it's been a while since we looked at this stuff. Remember that means x is equal to 4. So what does y equal? So when x is 4, read up, read across. So my function at 4 is equal to 1 because that's my y value. So that's just equal to 1. Okay, how about f at 19? Oh, 19 is not on my grid. It's over here somewhere. All right. Well, if I know a period is 7, then that means that 19 is going to have the same value as the point 17 before it. So let's figure out what 19 minus 7 is. Well, that's 12. So the function at 19 is going to be the same value as the function at 12. So it's going to be equal to a y value of 0. Huh. Okay, let's try that again and just make sure. So what's 12 minus 7? Well, that's 5. Back up 7 here. Oh, look, it's also equal to 0. Oh, cool. So function f is periodic if there exists a positive number p such that f of x equals f of x plus p for every x in the domain of f. So the smallest possible value of p is the period. So that's just a mathy way of saying that this value is going to be the same when I plus the period, plus the period, plus the period, plus the period, and keep working my way across. Amplitude is another very important word to know. So in any periodic function, the amplitude, hang on here. Okay, so in any periodic function, the amplitude is defined as half the distance between the maximum, so that's the biggest y, and the minimum, which is the smallest y. In other words, the amplitude is half of the total height. Okay, that's one way to look at it. The maximum values occur at the peak, so that's the top, and the minimum values occur at the trough, which is the bottom. Okay, and we're going to calculate that. Amplitude, it's going to be my maximum minus my minimum, and we're going to divide it by 2. One last important word before we move on, the equation of the axis of rotation, also called the axis of equilibrium, also called the midline, whatever, there's lots of words. It's the horizontal line halfway between the maximum and the minimum. So to solve for that one, we're going to take our maximum and we're going to add it to our minimum, and then we're going to divide it by 2. Okay, so let's do it. Here I have a nice, beautiful sinusoidal curve. I want to figure out the coordinates of the first peak, the first trough, the period, the amplitude, and the equation of the axis. All right, let's do it. So our first peak is going to occur here. because that's my top. Here's my second peak. Okay. So my first peak is happening when x is equal to 0 and y is 10. So 0, 10. Our first trough, so our troughs are down here. So there are bottoms. So that first trough, so this is at our minimum here. So that's happening when x is equal to 1 and y is negative 10. So there's my second trough here. Okay, so this y value here is my minimum. And this y value up here is my maximum. Okay, because that's my highest. This is my lowest. So my lowest is there. My period is how far it is between one peak to the next, or from one trough to the next. So my second peak is at when x is equal to 2. So if I subtract my x's here, 2 minus 0 is 2. So my period is 2. So it repeats itself every 2. I could have done that with my troughs. 3 minus 1, which also equals 2. Okay. Amplitude. So the amplitude is half the total distance. Okay. So let's figure that one out. Amplitude. We said we take our maximum, we minus our minimum, and we divide that by 2. Okay, so maximum minus minimum divided by 2. So our maximum is 10 minus a minimum, which is negative 10. Divide that by 2. So what does that equal? 10 minus 10 gives me 20. 10 minus negative 10 means I'm adding over 2, which gives me a total of 10. So my amplitude, I can draw it there or I can draw it there. And in both cases, it equals 10. Well, that makes sense. Okay. How about our axis? So our axis, we're going to take our max and plus our min and divide it by 2. So in this case, I take my positive 10. I'm going to plus my negative 10 divided by 2. Well, that's just going to give me 0 over 2, oops, which is just 0. So my axis is actually, in this case, not always, but in this case, my axis is the x-axis. Okay, that doesn't always happen, folks. Okay, so same question. Here we've got hours of sunlight in Windsor. So we want to do the same sort of thing. We want to figure out our crest, our trough, and all the good pieces in between. So our first crest, I would say, is happening around about here. And then our next one's happening around about here. Oh boy, these are tricky to see. So there's my crest. Okay, a trough is probably about here. So that's, remember, our lowest point. So coordinates for that one, I would say, is probably 365 and 8, 9. I'd call that 9. Oh, our first trough was actually probably over here at our y-axis. So that would be when x is equal to 0 and y is 9. So this would be our first trough. So this one would be our second trough. Here's our first crest. Here's our second crest. And they both have y values, I'd say, of 15. This, I would say, is about 535 and 15. And here, I would say, oh boy, that's a tricky one to read. I think I'd say that's at about 170 in my x-axis, 170, 15. So there's my crest, there's my troughs. Let's figure things out. So the period, I'd say maybe from here to here is my easiest points to read. So that would be from 365 minus 0. So it's 365 days. That makes sense. It's a year. Okay. My maximum value is my y value. So that would be 15. So I'm just going to write that out here. My minimum value is going to be the 9. So these are y values. So now I can figure out my amplitude. So that's going to be my maximum minus my minimum divided by 2. So 15 minus 9 divided by 2, what does that equal? 6 over 2, so 3. So my amplitude is going to be 3. My axis of equilibrium is going to be my maximum plus my minimum divided by 2. So my maximum was 15, remember? Plus my minimum, which is 9. Divide that by 2. What do you get? 24 divided by 2. So that's equal to 12. So at 12, I can draw a straight line. Stop that. I can draw a straight line across, a nice horizontal line across at 12. And there's my axis of equilibrium. And then my amplitude, so my amplitude here goes up 3, and my amplitude here comes down 3. So there's my amplitudes. Nice. So last but not least brings us to the good old sine curve. So sine x is the function that we want to plot here. So what I did is I just typed that into decimals, got my nice beautiful picture. And if you highlight onto here, you can see what some of the points are. So sine goes through 0, 0. This point here is at 91. This is 180, 0. Here I've got 270 degrees, -1. These are all in degrees, by the way. And last but not least, this takes me up to 360 degrees at 0. So sine is actually 0 several times. It's equal to 0 there. It's equal to 1 at 90, 0 at 180, -1 at 270, 0 at 360, and then repeats. And then to figure out the 45, again, you can go through in decimals, or you can just calculator that. So type in your calculator sine of 45, and you get 0.7. 0.7, 0.7, -0.7, -0.7. So you could calculator all of that, and you would get these answers. And then what we want to make sure that we know is, let's look at our domain of this function. So it goes forever and ever 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 and ever. It never ends. So this is valid for x is any real number. Okay, or if we want to talk about angle, we could say that in terms of angles is any real number. Whatever, same thing. Our range, well, until we start changing the curve around, the sine curve, so y is any real number such that -1 is less than or equal to y is less than or equal to +1. So there we see we have our minimum value and our maximum value of 1. So there's domain, there's range. What else did we want? Our maximum value, oh, we just said that. So y equals +1 at 90 degrees. And we reach a minimum value, so y is equal to -1 at 270 degrees. Our amplitude, so the distance from the x-axis to there is 1. Distance from the x-axis to there is 1, so our amplitude is 1. That's our 1. -1. So our amplitude is 1. And our axis of equilibrium, right? We're going around the axis, so we're going around the x-axis. So our axis of equilibrium is our x-axis. Okay, so we're bouncing around it. So that's our midline. Period. So we see that it repeats itself after 360 degrees. Our x-intercepts we see happen here, here, and here. So these are all our x-intercepts. X-intercept, x-intercept, x-intercept. So our x-intercepts at 0, 180, 360. 0 degrees, 180 degrees, 360 degrees, and our y-intercept, what goes through the origin here, so that's at 0, 0. And there you have it. There's the sine curve. We're going to play with that over the next few days, so just kind of get comfy with it, please.